Sorry, guys. There we go. Okay, so again, I just asked you guys to look at your formula sheet and see that you don't have to memorize these formulas. When you're asked to do water potential problems, you just look in that same spot. The formula sheet will be exactly the same as the one that is given to you guys, okay? So the plant cell water potential is 2 bars, and its solute potential is 3.5 bars. What is the resulting water potential? And this is a formula that we're going to use, and I'm going to write it out. So when I post the key, students will understand how we got to the answer. So water potential is your pressure potential plus your solute potential. So just plugging in, we're given all of those for this first pretty easy problem. So we'll just plug those all in. Now on the College Board, you're saying to yourself, do I have to write it out the way Mrs. Hill-Manson's writing it out to get the full amount of points? No. Math problems in the College Board is you just have to key in the bubble sheet the correct answer. I suggest writing these out when you're working them if you need to, so that you can catch it if you get an answer wrong. Okay, there should be a plus sign in there. So this should be your water potential and your solute potential added together. Okay, I forgot that plus sign. So we have negative 1.5 bars. I'm not going to explain that one. I think you guys should be able to see that math pretty clearly. Next story problem is, the plant cell from question number 1 is placed in a beaker of sugar water with a solute potential of negative 4 bars. In which direction will the net flow of water be? So I strongly suggest when you're doing these problems to write out a visual. Okay, so give yourself a container. There's my beaker. Doesn't have to take very long. And then put your cell inside of that beaker. Okay, so they tell us that the cell is negative 1.5 bars. So even if you don't write units and you're just sketching it out for yourself so you can visualize in case you're asked other questions, which I'm going to ask you right now. So the cell is 1.5 bars, and in this problem, they say that the solution is negative 4 bars, right? So which direction would the net flow of water be? Will you guys yell out into or out of the cell? Everybody yell something? Yeah. So the water will move to where we have a more negative solute potential. Okay? So it's going to flow out of the cell. Let me throw down some other questions that they might ask you. They might ask you the tonicity of the cell. So what would the cell be? Hypotonic or hypertonic? And they might call that the tonicity of the cell. Yell out your guess now, knowing it's okay if you're wrong. Hypo or hypertonic, yell it out. It's hypotonic, right? Here's a memory aid that you might remember from the video. I don't know if they said this one or not. Hypo has more H2O. So think of that O in hypotonic. And remember that that's going to have more H2O, okay? So water would move out of the cell then because there is more water inside the cell. It moves from high to low concentration. Another thing that they might ask you if you did a math problem like this or you were presented with this information is that they might say, what is the solution? Yell out what that is, you guys. Want me to give you choices?
Hypertonic.
Yeah, hypotonic, it would be what? It would be hypertonic, okay? Another thing, another memory aid they gave you in the Ed Puzzle video questions. I think this was like that teacher that did the 20-minute long video. He said solutes suck, right? What does that mean? That means that if you have more solute in a solution, then it's going to draw the water towards it. So solutes suck. So that would be a hypertonic solution. They might say something like, where do we have more solute? What would you say? Inside or outside of the cell? Yell out your guess. It's okay if you're wrong. You say outside. Very good. Okay, so that's kind of the idea with that. All right, the original cell from question number 1 was placed in a beaker of sugar water with a solute potential of negative 0.15 megapascals. And then they tell you that 1 megapascal is 10 bars. So you need to know how to do conversions in order to make sense out of what you're given. So it's the same thing as the first. So that cell is still the same. Now we have to figure out what the solution would be when we convert it from megapascals to 10 bars, okay? So if, I haven't taught chemistry in about 10 years, but this is how I used to teach conversions. You write out your given, and then you put the units that you want to get rid of on the bottom, and the units that you want to end up to on the top, and then you apply the conversion. You don't have to memorize that. You would be given that on the test, right? You don't have to memorize that conversion, okay? Now, if it's on the top, you multiply. If it's on the bottom, you divide. Or you can just slide the decimal place in this case. And you get rid of the units that don't belong. Is that how they still teach conversions? Those of you guys that have had chemistry? You guys sort of all had chemistry. I think in regular chemistry they still do conversions, right? Or did we miss that because of the pandemic? Is that how they teach conversions? That's how I used to teach it. I don't even know if they teach it the same. Maybe they went like this, right? I don't know. Okay, so you should be able to do conversions in ecobology. So that is the outside of the container. Hey, look at that. That looks very familiar. Now, when they give you a situation like this, how might you describe, what words might you use that would be good for this? Yell out some guesses. Yeah, you might say that it's isotonic. So we can write that down if you had to describe it in a paragraph. What's another thing that we might say? What is an isotonic solution to be considered? Maybe you're not sure. Yeah, what kind of equilibrium? Yes, dynamic. If you weren't sure of this, write it down right now. I gotta write until I'm saying dynamic. That's an M-I-C. Okay. What does dynamic equilibrium mean? Right. She said that the net flow between the molecules is staying balanced, okay? The reason that we don't just say equilibrium and the reason that we say dynamic equilibrium is because it's still moving, right? When we teach osmosis and diffusion, a lot of times students think that things just get frozen in place, right? Once they're balanced, it's a math problem, done, we're done. Nothing moves anymore, and that's not the case. In life, molecules and particles are always moving. So I want you to realize that there's still movement between the particles and the membranes, but it's not a net flow. That's the word that we use. It's not a net, everyone's not rushing into one direction and we're not going to change one side versus the other. But that's why it's important, maybe when you're writing this out in an essay, that you don't just say things are in equilibrium. We call this isotonic. If you tack on that word dynamic equilibrium, your AP grader is going to know that you truly understand osmosis and diffusion. Because by putting dynamic equilibrium with isotonic, you're letting them know that things aren't freezing in place. You're letting them know that we still have some movement. So write those words down there so that you remember kind of what those things mean. Okay, we're going to get a little more complicated with our water potential problems because we're going to add concentrations of solutions. The value for water potential in root tissue was found to be negative 3.3 bars. If you place the root tissue in a 0.1 molar solution of sucrose, hint, hint, at 20 degrees Celsius in an open beaker is also a hint, we're going to use that in our problem. What is the water potential of the solution, and in which direction would the net flow of water be? So the moment that you see that there's molarity there, that should be your signal that you need to use the second water potential problem. So let's go ahead and write that down. And again, this is nothing that you need to do. I think it's kind of a good rule of thumb when you're processing these math puzzles to write down the formula that you're using so you can make sure you don't miss something. But it's totally up to you. I know some people have wonderful math brains and they don't need to write anything down and they still get their answers right, okay? Did I hit record? Oh, I did. All right, so let's plug in what we're given in the formula. First thing is our I. What does that mean? Or what should it be? Tell me the number it should be for this problem. Just yell it out.
1.
We're small enough that we can have a conversation. Why did we choose 1? 1 is correct. Don't forget that negative because that'll screw you up. Why did we choose 1? Because it's sugar and sugar doesn't break apart, right? What would we choose if it was a salt? We'd choose however many pieces that salt has in its formula. NaCl would be 2, magnesium chloride, because it's MgCl2, would be 3, okay, etc. So that's our 1 there. C, what does C stand for? You guys yell out your guess. Decimolarity, which they tell us in the story problem is 0.1. What's our R? That is when we grab our formula sheet, and it's nothing we need to memorize. It's our constant. Yeah, plug that sucker in there. If you don't have a calculator, I may ask you to tell me what this is, because you're following along and you're punching things in. So maybe pull out a calculator and punch these in as we go along. And then the last part of the formula is our T. What should we put for our T here?
293K.
Yeah, why did you pick that?
Because the temperature in Kelvin is always 273.
Yeah.
And then plus the 20 degrees Celsius.
Right, so they tell us it in Celsius. That doesn't work for math problems. We've got to add 273 Kelvin to it to get the number that we need to use. Again, you don't have to memorize that. Look, they give it to you. Thank you, College Board. Okay, so plug that all into your calculator if you did not already set it up this way. I saw that a lot of you guys already did set it up this way, but once you get all of those numbers plugged in, what is your solute potential? Anthony, what'd you get?
Negative 2.43.
Yeah, negative 2.43 bars. Good. Now that seems like, okay, we're good. We can put our answer down now, but actually we're given our solute potential. So I just want to talk about this a little bit. For this problem and this problem and this problem, I worked the whole water potential as my solute potential as if it was water potential. Here's why. Does anyone know why? Why is my solute potential exactly the same as my water potential? Hello?
Because in an open container, the solute potential of the water, the pressure potential is 0.
Yes. In an open container, your pressure potential is 0, okay? So keep that in mind. So I'm just going to put that down in a formula for you guys in case you're wondering, hey, Mrs. Holmanson, why are you pretending like water potential is the exact thing as solute potential? This is the reason why. Our water potential is our pressure potential plus our solute potential. But if it's an open container, if it's a beaker, or if it's really not a plant cell, then it's going to be 0. So if it's 0 plus my solute potential, which is negative 2.43 bars, it's going to be the same thing, okay? Just to clarify that a little bit in case you guys were wondering or you thought it was more complicated and then we were missing something. So again, let's plug in what they tell us in the story problem. They tell us that the cell has 3.3 bars. And now we figured out that the water potential of the solution on the outside is negative 2.3 bars. Overall net movement, yell out into or out of the cell. It's okay if you're wrong. Into, yes. Water is going to move to where we have lower water potential, okay? Or where we have more solute, because solutes suck, okay? Alrighty, let's move on. Next problem, sodium chloride dissociates into 2 particles in water. I doubt the College Board will tell you that. You should know that, right? That was a little hint, because this is our first worksheet. So the solution in question 4 contained 0.1 molar sodium chloride instead of 0.1 molar sucrose. So the only change in this whole problem right here is the number of particles, okay? So yes, I could plug this all in and write this all out right here and make that a 2, or if I'm a math whiz, how can I do that quicker? Yes, I take my answer from here, and if I'm only changing that to a 2 right here in this formula, I don't need to waste my time because the College Board test is a time test. And if I can figure out ways to do things quicker and get answers right quicker, I'm not going to go through all the steps because all they're going to ask me to put down is the actual final answer, okay? So that's why that second question is negative 0.487 bars. We took our previous answer and we just made the I. We changed. Did you guys know that triangle means change in math? Did you guys know that? Okay, so if you want to write down notes quicker every time you want to write change, you can make a triangle. I think maybe that's calculus. I don't know when you learned that. So triangle means change. So we're changing our I to 2 from the above equation. I'm just writing this down for the people that look at the key and they're not sure how we got that from the above. Boop. Okay, so let's draw a picture so that I can ask you other questions that you might have in like an essay or something like that. So here we have negative 3.3 bars in our little story problem. And here we have negative 4.87 bars. Overall net flow of water, yell into or out of the cell?
Out.
Yeah, it's going to move to where we have a lower water potential, a more negative water potential, where we have more solute, right? So they might say, what is the cell? What is the tonicity of the cell? Yell out what you would say to that. It's okay if you're wrong, yell something though. Yes, or whisper it quietly. That's fine too. The cell is hypotonic. Good. And then they could ask you the same question. What is the solution? And you would say the tonicity of the solution is hypertonic. Awesome. Okay. Yeah, kind of add those to this question so you can kind of practice that. Okay, we're going to get a little harder in the next two problems. A plant cell with a solute potential of negative 7.5 bars keeps a constant volume when it's immersed in an open beaker that has a solute potential of negative 4 bars. What is the cell's water potential? Let's draw a picture so that we can ground ourselves and visualize this math problem and get a little more right-brained. Okay, so there's our open container, and in our open container we have negative 7.5 bars. Right? Okay, and then on the outside of the container, they tell us solution has negative 4 bars. So now we have to figure out the water potential. So this is just a straight up water potential problem, just using the more simplified formula. So what would the water potential be at equilibrium? Yell out your guess. It's okay if you're wrong. Give me what you guys got. Yeah, I heard you guys. It's 3.5 bars. Good. Equally, I can't write and talk at the same time. Okay. Next problem is a bit of a thinker. Okay. At 20 degrees Celsius, a plant cell containing 0.6 molar glucose is in equilibrium with its surrounding solution containing 0.5 molar glucose in an open container. What is the cell's water potential? So depending on how you want to approach this, you want to figure out the surrounding solution first so that we can use that information to calculate the cell at equilibrium. So what I'm going to do first is I'm going to calculate the surrounding solution's water potential. So the surrounding solution's water potential, we need to use our water potential formula, and remembering that that is pressure potential plus solute potential, okay? Now, since we're given all of this molarity, we have to use the solute potential formula where we're plugging in molarity. So to get this part of the equation, we need to plug in our negative I CRT. So, and then this is, what is water potential going to be for this one? That's going to be 0, okay? All right, so let's figure this out. What is our I? It's 1. Yeah, don't forget that negative. I'm going to turn that into a 1 because I started to make my parentheses a little too soon there. And then our C. Yell it out, everybody.
0.6.
We're starting off with a solution. So we're going to do, just because we're calculating for the solution first so that we can get to the equilibrium. Yeah, so that's when we're going to do the 0.5. Okay? Because that's what we're starting with. And then what about our I? We know that that is negative 0.831. We don't have to memorize it. And then, Peyton, what did you get for temperature for this one?
293.
293. If you didn't set this up, if you were like, I don't know how to start this, I'm going to write a few words down so Mrs. Hillmanson thinks I tried, that's fine. Punch this into your calculator right now the way that I've set it up so you can tell me your solute potential. Okay? Take a moment and punch that in. And what do you get for that? Lamb, what do you have? Need a moment.
It's
So you're just calculating your solute potential. So -1 times 0.5 times 0.0831 times 293. Got it? Do you want me to talk you through it again?
No, I multiplied, but I used 0.176.
Okay, so I'm gonna come back to you in a sec, okay? Braden, can you tell me what you got for that, for the solute potential?
Negative 12.72.
Yeah, I think I just rounded that, so I wrote -12.2 bars. Now you're gonna take this -12.2 bars and you're gonna use that as your water potential of your cell, because they tell you in the story problem the cell's it's at equilibrium, right? So now you have your water potential for your cell. So you have this part of your equation for your water potential, okay? So now we want to do the same thing. We need to calculate the pressure potential for this, okay? So the pressure potential for this cell, and there is going to be pressure potential because it's a cell, it's a plant cell, right? So plant cells have pressure potential. Why do plant cells have pressure potential, but open containers and animal cells do not? Cell wall, right? That cell wall can contain that pressure. Okay, good. So we're going to plug in all of our information that we have for our solute potential, okay? But what's going to change in this? Everything is the same. It's still sugar, so our I is the same. What about our molarity? Is our molarity the same, Anthony? We're doing our cell here. This is the
Yeah.
cell at equilibrium.
Molarity would be 0.6.
Right. Molarity is not the same. It's going to be 0.6 now. Okay. R value is always the same. And temp didn't change. So we plug those in. All right. Now we want to get our solute potential so that we can solve for our pressure potential. Plug that into your calculator. That's why I'm pausing, in case you didn't get that. What do you get for that answer? Jason?
I rounded to 14.7 mark. Negative 14.
Yeah, I mean that's pretty good. I don't think the College Board would care. I have 14.6, but yeah, it depends on kind of where you round. And the College Board for biology doesn't care about significant figures. I don't even know if they do for chemistry anymore. Okay, so that should do. I'm just gonna work it from my 14.6, but that's close. Okay, so now I solve for my unknown. So this is just like an X, solving for my unknown, right? So now, what is my water potential? Emma? 2.4 bars. All right. Okay, I think that would be that might be even harder than the College Board would give you, okay? But it's a nice challenge, so I may give it to you on a test or quiz, so kind of be aware of how to solve a problem like that, okay? All right. So now, if you guys could switch over to the the Google Classroom for AP Biology, so I can let you know where we're going after you finish the packet that you're working on. And you guys said you're still on page 2 or 3 maybe. We haven't finished the packet yet. So looking at the Google Classroom site, you'll see that there's a spot for you guys to make your own virtual groups for the lab that we're going to do. But in order to understand the directions for the lab that we're going to do next week, you need to look at the very bottom of the packet that you were looking at. So there's a paragraph there on the bottom that once you finish, it'll tell you what to do. Okay, so after you have answered all those questions, and I'll go over them on Monday. So make sure you finish trying all of these questions on Monday I want to see an honest effort on Monday so that you're staying with where we're learning. Then you'll see there's a prompt. It says design a lab to test the sugar concentration in a plant, fruit or root of the plant. I'm going to give you some that I know work well for this, but that's not to say that you couldn't be like, hey, Mrs. O'Manson, what about this? Could we try this? Run it by me. Some do not work and some do work. And you'll see that. So these are the things that you should be thinking about. What part of the plant are you testing? You'll have that answer when I show you where to go on Google Classroom. And how will you test the concentrations of that plant part? Okay, so we're looking for the sugar in the plant part. What lab supplies will you need? I will tell you that we have different molar concentrations of sucrose already prepared that might be helpful in helping you figure out what the concentration of sugar is in your plant cells that you choose, okay? So these are all available, and I can lead you in the right direction when we are designing on Monday, but I want you to think about how you might do that. How will you determine the unknown sugar concentration in your plant part? Okay, so next thing you do is you go to Google Slides that are found on Google Classroom. They're bigger. Open up that Google slide, and this is a shared slide. So please don't change the formatting, because that's going to change it for everyone. This is where we're going to organize ourselves into virtual groups for this lab. Why aren't you going to my computer? There we go. Okay. And everybody open that. Bada boom. Okay. You guys can type on this, right? Okay, good. So you go. Nobody put themselves in groups yet in third hour, and it's okay. Oh, yeah, they did. Okay, fun. Okay. So we are fourth hour. Okay? Good. You guys are all there. I can see you. Okay. So my suggestions. I know potato cells work for this. Carrot cells. Apple cells. Something of similar consistency would also work, right? Any root or any fruit that is of similar density should survive, so that we could determine this. So then you have another spot where it says other choice. Like I said, don't just randomly put one down there. Run it by me to make sure. We have a minute until the bell, right? Okay, you know what to do. Finish that packet, go on there and join a group, okay? I will see you guys Monday. Make sure that packet's done and you've joined a group on Monday. We'll sort that all out and set up the lab Monday.
I didn't
You're
get
missing
a
a
full
page.
pack. Yeah.